So in this question, they're saying that the density of a 3 molar solution of Na2S2O3, so they're talking about the hyper solution, is 1.25 gram per ml. Cool. Calculate the percentage by weight of Na2S2O3 and the molality of Na plus ion. Okay, fine. So, very first thing is they have given you the density. They have not given you any, they've given you the molar concentration. They've not given you any volume. They've not given you any weight, but that's fine. We can assume and we can, find out per liter and we can go ahead from there. So, let's see. So, first I'm going to assume volume is equal to 1 liter, which is nothing but 1000 ml of this Na2S2O3 solution. Okay, you have your Na2S2O3 sodium thiosulfate solution. Okay, now what have they said? They have said that concentration is equal to 3 molar. What does that mean? It means that you have 3 moles of Na2S2O3 in 1000 ml of solution. Fine? Solution, important. This is given to you. Now they have told you that the density of this solution is 1.25 gram per ml. So if I take 1000 ml of solution, then the weight of that solution will become what? It will become 1000 multiplied by 1.25, which is nothing but 1250 grams. So your weight of 1 liter solution is 1250 grams. Out of this 1250 grams, you have 3 moles of Na2S2O3. So you can find out what is going to be the weight percentage of Na2S2O3. First you have to find out the weight of Na2S2O3. This is going to be weight of solution. Okay, so this is going to be 3 into molar mass of Na2S2O3. What is it? Okay, you have to calculate. So sodium you will take 23 gram per mole, sulfur you will take it as 32 gram per mole, oxygen you will take it as 16 gram per mole, and when you calculate you will get 158 gram per mole as the molar mass of Na2S2O3. Fine, multiply this, you will get 474 grams. Okay, so this is the weight of Na2S2O3 in the given 1250 grams of solution. Okay, fine. So now what do we have to do? We have to calculate the percentage by weight of Na2S2O3. Okay, so let's do that. So percentage by weight. Okay, this is going to be what? This is going to be 474 divided by what weight will you take? Will you take weight of solvent or will you take weight of solution? We have to take the weight of solution, right? So you take 1250 and since it is percentage, you multiply it by 100. I am approximating this 474 to 475 so that I can cancel it by 25. Okay, so 25 into 20 is 500. 500 minus 25 is 475. So then I will cancel this. I will say this will go 19 times and this will go 50 times, right? This will go once, this will go twice. Your percentage by weight is 38%. You have 38% by weight Na2S2O3 in the solution. 38% is the percentage of this Na2S2O3. Okay. Now, I said that in 1250 grams, you have 474 grams of what? Na2S2O3, which means the rest of it is water. Agree? Okay. So when you calculate, what will you get? You will get, let's see, I'll quickly calculate it here. 474, so this will be 10, you get 6, this will be 4, 1, and here you will have 11, so you will have 7, you will have 7, 776. Okay, so here you're getting 776 grams of what? Solvent. What is your solvent? Water. Okay, even if it were any other solvent, doesn't matter. You have 776 grams of solvent. Okay. Now, this 776 gram of solvent had 3 moles of Na2S2O3. Okay. So, 3 moles of Na2S2O3 will give you 6 moles of Na plus ions. Correct? Okay. Which means you have 6 moles of Na plus ions in 776 grams of solvent. How many moles of Na plus ions will you have in 1000 gram of solvent? Find out, and that value that you find out will be your molality. You are required to find molality of Na plus ions. Okay, let's solve. You have 6 into 1000 divided by 776. Okay, now what can you do? See, You can see, you know that 1000 by 750 is 3 by 4. Okay, 750 plus 25, right? You have 776, so I can write it as approximately 25, right? So this will be it. Okay, now what can you write it as? You can write it as 3 divided by 4.1 roughly. Okay, sorry, this will be 4 by 3, my bad. 4 by 3, so now you can write it as 4 by 3.1. Okay, so this will go 4 times, this will go 3.1 times, which means what? Which means now I can cancel this, I can approximate that to 3. Okay, I approximated that to 3 and I got 1 and I got 2. So your molality that you're getting is approximately 8 molal, but you need to take that with a pinch of salt because you have done a fair share of approximation by making your denominator 3. If you make your denominator 3, you are effectively talking about 750 grams of solvent to begin with, which is okay. Like, you know, you might encounter some discrepancy. So the value of molality that you'll be looking for will be less than 8, but it has to be more than 7.5. Okay, so I want a value of molality which is less than greater than 7.5 but less than 8, something along these lines. Okay, now we want 38% concentration of Na2S2O3 by weight, which is here in option B. So option B is sorted. A, C and D, they're all pretty far away, so you can discard it anyway, right? And you got 38%, you're given 37.92, so that's a, you know, very good number. Now next you have molality of Na plus. Okay, we want something that's close to 8 but slightly lesser. Between 7.5 and 8 is the value that we're looking for. That is also matching. You have been given 7.73. Okay, look at your other options. You have 3.86, which is half of the value. Okay, so if you made the mistake of taking molality of Na2S2O3 instead of molality of Na plus, then you will get this answer as 3.86. Okay, but anyway, so here your options are fitting in pretty well. So option B is going to be the right answer to this question. Alright, so take a look at this question. Here they're asking us for the factors that influence the ionization energy. Okay, so you have option A, size of the atom, option B, charge in the nucleus, option C, inner electrons which effectively screen the nuclear charge, option D, all of the above. Okay, so first let's talk a little about the ionization energy trend as we observe it in the periodic table. Okay, so what happens to ionization energy as you move down the group? This is pretty simple. As you move down the group, what happens is the size of the atom increases, and as the size of the atom increases, we can say that the ionization energy increases. Sorry, ionization energy decreases, right? Which means the amount of energy that is needed to remove an electron from a neutral, gaseous, isolated atom is going to decrease, right? That's the definition of ionization energy. Now, as you move from left to right in a period, what happens? Left to right across a period or along a period, what happens? We know that the size is going to decrease. The size decreases because of which the ionization energy increases. One other factor that we need to talk about here is the Z effective, right? Effective nuclear charge. So from left to right, your effective nuclear charge increases. Okay, your effective nuclear charge increases because of which the ionization energy increases. Okay, you need more energy to overcome the attraction between the nucleus and the electron. Okay, so yes, this is what happens. Now let's attack the options again. So size of the atom, yes, most certainly this does influence the ionization energy, because when you talk about size of the atom, you are talking about distance from the nucleus, distance of the last electron, the final electron, the outermost electron from the nucleus. So if it is further, then the attractive forces it will feel will be lesser. So because of that, yes, if your size of the atom is increasing, you need lesser energy to overcome the attractive forces experienced by the electron due to the nucleus. Okay, so yes, this is definitely something that influences ionization energy. Then we have option B, charge in the nucleus. That is nothing but we are here talking about your Z effective. Okay, your Z is increasing, right? If I say you move from left to right across a period, what happens? Atomic number increases, so Z increases. Okay, and your electrons are being added to the same shell, right? So you have you have electrons being added to the same shell. So you have Z effective is equal to what? Is equal to Z minus sigma. Your sigma is the same. That is screening effect. Okay, Z is increasing. So what happens? Effective nuclear charge is increasing. So yes, ionization energy will increase. So charge in the nucleus does affect the ionization energy. Okay, then lastly we have option C, the inner electrons which effectively screen the nuclear charge. Now here we are talking about the screening effect. Okay, so what do we know? We know that S electrons have a higher screening effect than P, than D, than F, right? The order is S greater than P greater than D greater than F in terms of the screening effect that we observe. Okay, so yes, this is important and this is definitely something that affects ionization energy. And this is also something, this is, you know, a combination of factors B and C is what we see, which is responsible for the anomalies that we see in the ionic radius of aluminium and gallium, or in lanthanide contraction, right? So it's a combination of your effective nuclear charge and screening effect or poor shielding effect of F electrons, D electrons. Okay, all of these things put together give us a lot of effects that we already know of. So yes, all these three are responsible for the change in ionization energy, which means option D, all of the above, is going to be the right answer to this question. Okay, so here they're asking which of the following is or are correct. Right. So what is happening here? You have option A, double bond is shorter and stronger than a single bond. Okay, you know that this is true. Yes, you know that a double bond is going to be shorter in length, and the moment you say shorter in length, your the two atoms are coming closer and the energy between them, right? The energy of the system, basically the energy of the system is reduced, so it's a more stable arrangement, which means you need to supply more energy to break it, right? More energy to break it means it's a stronger bond. So yes, this statement is absolutely true. Then you have option B, sigma bond is weaker than the pi bond. Okay, option C is saying sigma bond is stronger than the pi bond. So these two are along the same lines. Let's dive into what is sigma bond, what is pi bond, and then we'll get the answer to this. So sigma bond, let's say I'm talking about my p orbitals, right? So this is my internuclear axis, which is the z axis. So here you have a p, here you have a p. I mean, wait, this is just terrible drawing. At least I need to be symmetrical. This is PZ, this is another PZ. Okay, so when they overlap like this, when there is a head-on overlap or there's a head-on collision of these two orbitals, then you can say that this bond formed is a sigma bond. Okay, this is your sigma bond. Now, same internuclear axis, Z is the internuclear axis. Now here you have your, let's say, perpendicular, right? So let's say PY, whatever it is. Now here, they have a lateral overlap. Okay, so in case of lateral overlap, it overlaps like this, right? So this is your pi bond. Okay, I'm not drawing overlapping figures because that will become really messy. I'm confident about that because of my drawing skills. So anyway, what you need to take away from here is that in sigma bond you have a head-on overlap, right? Your effective overlap is more. Okay, whereas in a pi bond, what happens is you have a lateral overlap, right? So the overlap is very less. Okay, so because you have a head-on overlap in the sigma bond, okay, because you have a head-on overlap in the sigma bond, what you can say, okay, you have an axial overlap in the sigma bond, what you can say is here your effective overlap is more, hence the bond is going to be stronger, because if the effective overlap is more, then the overall energy of the system of two atoms, whatever our two atoms are in question, that will come down. Okay, that will come down, because of which what happens, because of this, if you need to break a sigma bond, you need to supply more energy. So sigma bond is going to be a stronger bond than pi bond. I know that these are things we just say and we just take it for granted, but remember, it's very, very important to know why. Okay, so because of higher effective overlap, sigma bond is stronger than the pi bond. So this is true and this is false. Okay, so 1 second, this is true. Okay, all right, so you have two true statements, A and C both, which means option D, both A and C, is going to be the right answer to this question. Okay, so here they're saying the number of subshells present in the third shell is going to be equal to what? Okay, So third shell means what? Third shell means your principal quantum number n is equal to 3. Okay, and number of subshells means what? Number of subshells means they're talking about the number of values that L can take. Not what is the value of L, but how many possible values of L can there be for n is equal to 3. That is what they're saying. Okay, so what do we know? We know that L can take values from 0 to n minus 1. Okay, these are the values that L can take. Right? So here you have n is equal to 3, which means it can take 0, 1 and 2. Okay? This is what L can take, and you need to remember that when we talk about quantum numbers, apart from a spin quantum number, everywhere else we are only talking about integers. Okay? No fractions. Okay, so L can take values 0, 1 and 2. 0 will correspond to S, 1 will correspond to P and 2 will correspond to D. Okay? So how many subshells are present? SPD, 3 subshells. Okay, please don't go and write that, P will have 3 and D will have 5. That is not L, that is your M, that is your magnetic quantum number, that is your number of orbitals, number of subshells. Subshells, only 3. Okay, so option B, 3 is going to be the right answer to this question. Question, they're saying that for the disproportionation reaction, H3PO2 gives you PH3 plus H3PO3. The equivalent mass of H3PO2 is going to be what? They're saying that M is the given molar mass of H3PO2. Fine. So, very first thing you need to remember is that equivalent mass is nothing but your molar mass, which is given to you as molar mass M, divided by n factor for the given compound. Okay. Now, you need to, another thing you need to make note of very, very keenly is that this is a disproportionation reaction. First of all, what is a disproportionation reaction? Disproportionation reaction is one wherein, the same element of a certain compound is undergoing both oxidation and reduction simultaneously in that one given reaction. Okay, so for disproportionation reaction, how do we calculate the n factor? We know that 1 by n factor total, okay, is equal to 1 by n factor due to oxidation plus 1 by n factor due to reduction. Okay, cool. So now let's find out what is the oxidation half, what is the reduction half, so we can find out these n factors. So here you have H3PO2 gives you PH3 plus H3PO3. Okay. So now let's see. Okay, so phosphine is the easiest to deal with because hydrogen is going to be in +1, phosphorus is going to be in -3. Done. Let's find out the other two cases. So H3PO2, let's say P is the oxidation state of phosphorus. So P plus 3 minus 4 is equal to 0. So P minus 1 is equal to 0 or P is equal to +1. So here you have phosphorus is in the oxidation state of +1. Cool. Now let's talk about H3PO3. Okay. So here you have +3 due to hydrogen plus, let's say P1 is the oxidation state of this phosphorus in H3PO3. -6 is equal to 0. So P is equal to +3. So here, P1 is equal to +3. So here the oxidation state of phosphorus is going to be +3. Okay. Now you can see that here, one second. So here what happens is phosphorus goes from +1 to -3 and +1 to +3. So +1 to -3 is what? This is your reduction and +1 to +3 is your oxidation. Now find out the n factor for these respective changes. So first of all, delta OS, change in oxidation state for reduction is going to be -3 minus of +1. So -3 minus 1 is going to be -4. We only need the magnitude. So magnitude or the value that we'll be taking is going to be 4. Okay, cool. Now, what about oxidation? So change in oxidation state for oxidation is going to be 3 minus of +1, which is nothing but 3 minus 1, which is 2. Okay. Now, since you have only one phosphorus atom on the reactant side, this is, as good as saying change in oxidation state is your n factor because you just have to multiply it with 1. So, this is 4 and 2, right? So, now 1 by n factor total is equal to 1 by n factor for oxidation, which is 2, plus 1 by n factor for reduction, which is 4. Okay. So what do you have? You have 2 by 4 plus 1 by 4, that is nothing but 3 by 4, which means your n factor total is going to be 4 by 3. Okay, great. Now we have to find out the equivalent mass. N factor, we got it as 4 by 3. So your equivalent mass is going to be equal to m by 4 into 3, or 3m by 4, and that's here in option A. So option A, 3m by 4, is going to be the right answer to this question.